In this video, I'm going to talk to you about intermolecular forces, or IMFs, which are the attractive forces between molecules and between ions and molecules. Now, this is in contrast to intramolecular forces, which are the chemical bonds within molecules. I would like for you to get out your intra and intermolecular force sheet, as I will reference this throughout the video. Let's talk about boiling water. So what really happens when water boils? Are we breaking the covalent bonds between the hydrogens and the oxygens? No, of course not. What's happening is intermolecular forces are being broken between the water molecules. IMFs are weaker than intramolecular forces, in other words, bonds. So I wanted to make sure to really make that distinction here before moving forward. Intermolecular forces are between and among molecules, whereas intramolecular, we're referring to within a molecule, which would be the chemical bonds. So let's go ahead and compare the strength of an ionic bond compared to a covalent bond. So in these examples, we are talking about intramolecular forces because we're talking about forces within the molecule, i.e. the bonds. So ionic bonds result from electrostatic attractions of cations and anions, as you know. And we've talked about Coulombic attractions and Coulomb's law extensively. So at room temperature, these are usually solids, whereas covalent bonds result from the sharing of electrons, and these can be solids, liquids, or gases. So when comparing the relative strengths of ionic bonds to covalent bonds, we're going to be using examples such as melting points and boiling points and things like that coming up in the next couple videos. But there's a great amount of variation among the energy required to break ionic bonds, covalent bonds, and metallic bonds. And we're going to be talking about that coming up, but this video sets the foundation for understanding the difference between intra and intermolecular forces, as well as understanding the different types of intermolecular forces that exist. As you can see from your sheet here, there's a great variation and there's overlap between the different intramolecular forces, and the same will be true for intermolecular forces. So we have to take these on a case-by-case basis. First, let's talk about dipole forces. Now, in previous videos, you learned about dipoles. You learned about these differences in electronegativity within molecules that lead to a partial charge disparity, where one pole carries a partial negative and the other pole carries a partial positive charge. So, due to these partial charges, polar molecules will tend to orient themselves such that the positive pole of one molecule is close to the negative pole of another molecule. So on your sheet here, we're going to first talk about dipole forces before moving on and really talking about a special type of dipole force called hydrogen bonds. So here we can see two molecules that are polar. Now recall, to determine polarity, we're using the differences in the electronegativities between species within those molecules. So for example, hydrochloric acid or hydrogen chloride, if we compare the electronegativity to the hydrogen compared to the chlorine, we'll see there's overall a change in electronegativity that exceeds 0.5, and thus we would refer to this as a polar molecule. It's that unequal sharing. So these molecules will orient as such. And we can see it here as well. In fact, if we combine a bunch of these together, we can see all of the different intermolecular forces. Now, in this case, these are all dipole-dipole forces, but you can see there's a lot of these forces occurring. And again, these are between molecules or between ions and molecules. They are among molecules. I want to continue to make that point throughout this video. Now, here's a special type of dipole-dipole interaction or force, and it's known as hydrogen bonding. In reality, though, hydrogen bonding is nothing more than an intermolecular force. Now, hydrogen bonds are stronger than dipole-dipole bonds, but they are nothing more than a special type of dipole-dipole bond. And they form between hydrogen atoms and three highly electronegative species: oxygen, nitrogen, and fluorine. Now, there's a little way for you to remember this, and that is ET, phone home. Okay, so phone home occurs when a hydrogen is bonded to either a nitrogen, an oxygen, or a fluorine. Okay, now, I do want to say again, this is a type of intermolecular force. So let's look at some examples here. All right, so hydrogen bonds are intermolecular. Okay, so that means they're between molecules. They do not exist within. If we look at water here, in this case, water, you know from your Lewis dot structures that we have a electron group of a tetrahedron. We have a geometry of a bent. We have a bond angle of 104.5. We have two lone pairs there on the oxygen. And overall, we have a dipole in this molecule. So you've learned all that. So we're not talking about intramolecular. Those are covalent bonds between the oxygen and the hydrogen. It's between the water molecules. And in this animation, you can see these intermolecular forces or bonds forming. In fact, you see two forming here. That's because on the red, which represents the oxygen, there are two lone pairs, and each lone pair is capable of forming a hydrogen bond between, in this case, the hydrogens of an adjacent water molecule. All right, so shown another way here, you can see our structure, you can see the two lone pairs, and you can see the dashed red lines are the hydrogen bonds that are forming intermolecularly. Okay, you can see the relative strength down here on your sheet. Hydrogen bonds are stronger than regular dipole-dipole. Why? Because they involve these bonds between three highly electronegative species: fluorine, oxygen, and nitrogen. Okay, now I want to use another example here. This is a hydrogen bond, absolutely. Why? Because it's forming between the hydrogen of one molecule and the nitrogen of another molecule. So this is a hydrogen bond occurring between a water molecule and an ammonia molecule. Okay, now this nitrogen with its one lone pair is only capable of forming one hydrogen bond, whereas among water we could form two because of the two lone pairs. However, this would be referred to as a hydrogen bond, and notice that it is between the water and the ammonia. Let's talk about ion-dipole intermolecular forces. And as the name suggests, these are forces that exist between an ion, say a sodium cation, and another polar molecule, like water. So that's the example given on the sheet handed out in class. All right. So attractive forces between ions themselves. So we talked about dissolution and solvation. You've seen this animation now several times, and yet here it is again. This is an example of an ion dipole intermolecular force where these water molecules are surrounding, in this case, the sodium cation. Notice how the large electronegative oxygen is orienting toward the positive cation. Okay. So these are the forces that are responsible for overcoming the crystal lattice structure of ionic compounds and melting those compounds, or in this case, dissolving these compounds into an aqueous environment. Okay, so they are the force behind solubility in polar solvents. Okay, so the next example is an ion or dipole induced dipole. Okay, so this is the attraction between an ion or a polar molecule and a non-polar molecule, and they are inducing dipoles. All right, so non-polar molecules can form dipoles. They're instantaneous dipoles. They're always changing, but it's the valence electrons, as you know, are able to move around. As they move around, there's areas of varying electron density. So you can actually have a nonpolar molecule that has a negative region where those electrons have moved and leaving the other region of that molecule slightly positive. Now they're very quick, which is why we refer to these as induced dipoles. So they're very dynamic. Let's take a look here foremost at their strength. Relatively speaking, they are not strong, but the more of these that form, the stronger the overall intermolecular forces are. Here we have iron 2+ and diatomic oxygen. Diatomic oxygen is clearly nonpolar because the electronegativities completely cancel out. Same with diatomic chlorine. And in each case here, instantaneous dipoles are formed between either the ion, in this case down here, iron, or a polar molecule, in this case down here, hydrogen chloride or hydrochloric acid. Okay, dipoles can be induced when those nonpolar molecules move close. Okay, so again, referring to your sheet here, you see xenon, all right, a noble gas, and you see a molecule of water, which is a polar substance. So in this case here, this is a dipole-induced dipole. That's how you would say it. In the case of iron, you would say that's an ion-induced dipole. Or, yes, ion, not iron. Ion-induced dipole. All right, let's look at a schematic here. All right, what's going on? Well, here we have an ion, in this case a cation shown here, and an anion shown here. Now notice when these interact, there's an instantaneous pole or dipole that sets up in the nonpolar larger molecules. Okay, so this is showing that yes, they form, but they are always changing. Okay, which is why we refer to them as instantaneous dipoles, but it's still an intermolecular force, an attractive force that's occurring. Let's look at this example here of polar molecules interacting with nonpolar molecules, and you can see here the induced dipole that forms. It forms for just an instant, and then it is gone. And it's dependent on the dynamics of the interactions occurring between the polar molecules and the nonpolar, or the ions and the nonpolar molecules. So these are induced dipoles. London dispersion forces. These are a network of instantaneous dipoles. So I've just spoken extensively about the formation of instantaneous dipoles in nonpolar molecules. Well, LDFs are a network of these dipoles that occur. If we look at a schematic here, we can see these instantaneous dipoles forming. In this case here, they're forming between two non-polar molecules. That's what LDFs are, to distinguish between what we just spoke about. Dipole-induced dipoles are different. A dipole is inducing a dipole on a nonpolar. In this case here, two nonpolars are inducing instantaneous dipoles on each other based on their proximity, based on the attractive force. Here we see in this neon, we see these electrons going to one side. So electron density increases here. What happens to these? These electrons go to the other side because they're repelled by these. What's attracting these electrons? The nucleus, okay? The positive protons in the other neon. So we're seeing the electron-electron repulsion, and we're seeing also the Coulombic attraction that's occurring between the electrons in one nonpolar entity and the proton in another nonpolar entity, okay? So they are essentially going to change the density of the electrons, or the electron cloud, those valence electrons in neighboring molecules. Okay, they are instantaneous, and they also depend on the size of the molecule, because the larger the molecule, the more polarizable it is. All right, polarizable means that we're able to draw more electrons over to one region, creating a greater dipole. Okay, so the larger the molecule, the greater the LDF, because the greater the polarizability of those larger molecules would be. All right, and we're going to talk about this in the next video when I talk about relative melting points and boiling points and things like that. So these examples here, you might be tempted to say, wait a minute, these are extremely weak. Indeed they are. However, the more LDFs that occur, the greater the collective intermolecular force. So in the next video, I'm going to talk to you about hydrocarbon chains. And among the carbon and hydrogen, that's a nonpolar bond. And intermolecularly speaking, we get LDFs forming among them. But the longer the hydrocarbon chain, the more LDFs, and thus the greater the intermolecular forces collectively exist. So it is no surprise here that collectively IMFs and LDFs, collectively LDFs can become the dominant intermolecular force. And here we have diatomic iodine showing, again, we see on this pole here we have a partial negative charge, whereas on this pole we have a partial positive charge, and that's where we get this LDF forming among them. Again, not within. Within, these are covalent bonds. Among, these are London dispersion forces, which are a type of van der Waals interaction. So there is a problem set that corresponds with this video where you're going through and assigning the different intermolecular forces and distinguishing between intermolecular and intramolecular as we continue to talk about our Georgia standards of excellence dealing with interactions of inter and intramolecular forces. I'll see you guys in class.